Today we're going to talk about the expansion and contraction of water and how that compares to the expansion and contraction of other materials. We have been talking about how molecules move in the states of matter, like solid, liquid, and gas. In solids, the liquids are moving much less and are typically very close together. In liquids, the molecules are moving a bit more and are a bit farther apart. In gases, the molecules are moving much more than in the previous two states and are taking up a lot of space. However, water molecules are an exception to this rule. When water molecules move from liquid to solid, the molecules actually begin to arrange themselves in a crystal pattern or arrangement. Those of us who live in areas where there is snow and ice may have experienced the solid crystal structures of solid water in the forms of snow and ice. Maybe you've been lucky enough to see the crystal structure of a hoarfrost or of a snowflake. So here are some of those structures. In solid water, the molecules arrange themselves in a pattern or grid, and that creates a little bit more space between them than they do in the liquid, but less space than they do in the gas. Between the solid state and the liquid state, the water molecules are actually less dense. They're farther apart because they have more space between them. That physical property of water gives solid water or ice two other physical properties over liquid water. Because the solid water, the ice molecules, are farther apart than the liquid water molecules, the molecules expand, not contract when they cool. Solid water takes up more space than liquid water. You have maybe witnessed this if you have left a beverage like a soda or water in your freezer for too long to chill it. You've seen the amount of force that expansion can exert on something. It has either exploded or pushed the ends out of the can. We'll see how this has played an important role in earth weathering and soil formation in a moment. This property also means that ice is less dense than liquid water, meaning that solid ice floats on top of water. We'll see why this is an important property of water that is critical for life in the cold and frozen areas of the world in a moment. You may have witnessed this if you have ever had a beverage with ice in it. The ice floats on the water. Most other solids will sink if placed in a liquid of the same material until they become the same temperature and therefore the same density and mix. So here you see an image of ice floating on top of a glass of water and of an iceberg, and you may have seen or heard the expression tip of an iceberg because only a small portion of it is above the surface, but a lot of it is there right below the surface, floating on the water. So let's talk about why this is such an important concept to learn in a science class, and why this is so important to life. So if we use the Celsius scale, you may recall that water freezes at 0 degrees Celsius. So let's say that we are at a fall or winter day and the outdoor temperature is 10 degrees. And that means that over a period of time, eventually the water will become 10 degrees Celsius as well, right? They'll both become the same temperature if the temperature remains stable long enough. So it's getting colder and cooler out, and the temperature is starting to drop more and more. And so soon it'll be 9 degrees, 8 degrees, 7 degrees, etc. That means that the temperature of the water is also starting to drop. 9 degrees, 8 degrees, 7 degrees, 6 degrees. The surface of the water will drop first, right? Because it is exposed to this cold air, whereas the water under the surface, closer to the ground will insulate it and produce some heat. So this ground is maintaining some of that warmth or insulating it. Let's just move those numbers out. All right. So we have water dropping in degrees here at the surface of the water. Now, when it hits 4 degrees is actually the most dense that water gets. So those water molecules are packed really tightly together now. they're at their closest form. So that water, because it's more dense, will start to drop. And this water here that is perhaps at 6, 7, 8, 5 degrees or so is less dense. So as that 4-degree water starts to sink, it will push up that warmer water, which means that now we are back to, instead of having 4-degree water, we're back to having 5, 6, 7, or 8-degree water, which if the cool weather continues to be next to the surface, so if we are at 4 degrees outside or 3 degrees or 2 degrees or below freezing temperatures, that means that this 5, 6, 7, 8-degree water will start to cool, and it will become 4 degrees again, and the 4-degree water will start to sink and pushing up this 5, 6, 7-degree water until that 4-degree water brings that 5, 6, 7, 8-degree water down low enough that it becomes cold enough. There's enough 4-degree water that the water down here is 4 degrees, and it has pushed up here the 5, 6, 7-degree water, right? Or that 4-degree water now is all the same, and pretty soon we have 3-degree water. But as I said, 3-degree water is less dense, so it is not dropping, and the 4-degree water is staying below. Then that 3-degree water becomes 2 degree, becomes 1 degree, becomes 0-degree water, which is ice. So the ice, as we just learned, is less dense than liquid water. So ice at 0 degrees starts to form at the surface here, and it locks in the warmer temperature water below. 4 degree, but now that water might fluctuate a little bit because it's got a layer of isolation above it on that ice, and we still have some earth creating some heat down here as well. So that water will vary in temperature around 4 degrees, but that the ice will continue to form. And if we get more cold days, so winter has continued, we've gotten more cold weather blowing in, creating a lot of cold temperatures. We're at 0 degrees, perhaps we're at 10 degrees below. That might mean that the ice will start to form deeper down. Pretty soon we'll be at 4 inches, 6 inches, 12 inches, and you'll be able to head out with your ice fishing gear and drill a hole into the water. Your hole would rather be on the surface of the water, on the surface of the ice, I suppose. And you can sit out there with your ice fishing pole and fish away for some of those fish. The great thing about this is that because the ice is less dense and it freezes at the surface of the lake, that means that all of this life can exist below the surface of the water. As I said, we get cold seasons where perhaps it'll get really deep, but then those animals like that little turtle will live in a little bit of a smaller place. Those fish will start to come together and congregate together in a smaller area. Their own life will continue to sort of create some heat underneath that lake. If we're under a river water has energy to it. That energy makes it much harder, as we know with molecules moving, makes it harder to slow moving molecules down, takes more energy, and they've got energy because of that movement. So river water tends to not freeze, moving water tends not freeze. This is why you maybe have been told if it's a really cold winter night and you live in an area where it freezes, you may have been told to leave your water running, just leave a little drip so that the pipes continue to remain running and the pipes won't freeze through as solid. This is also why we're told that river water is never safe, that walking out on a frozen river is never safe because you don't know where there might be a current underneath that water, underneath that ice, and that ice might be really thin because of that current, because that moving water has enough energy in it and isn't quite frozen through. So a couple of reasons or ways that science is important and it is meaningful outside of the school is that it explains why life is so important, why water is so important to life, why the properties of water, that it freezes, that it is less dense and therefore on the top of liquid water, is so important to life. It also reminds us not to trust river water, and the rules of thumb that if you live in a cold area and the temperatures are really cold and you might have pipes that are exposed to that cold temperature, why you should keep them running. Or if you have a faucet or hoses, you drain those in the fall so that water trapped in there doesn't expand and crack like we saw in the soda can. That water expands when it's cold, and that can cause a crack in a pipe or in a garden hose or in a faucet. So the next thing I wanted to talk about also is why it is so important, why this property of water is so important to our soil and why it has been important to life in this way. So as water gets into a small crack, it will freeze, and as we have discussed, it expands, which means it pushes out, so it drives a bigger crack, okay, called frost wedging, and eventually that crack breaks apart and you get a big space or a big gap in there. And you can see the evidence of some of that cracking, that water getting in here, so water dripping down from above can expand and crack and start to break away at these pieces. This is weathering. This has been one of the properties of life in that it has made more of the calcium and carbon that is locked into the earth available by breaking it down into smaller pieces. Previously, it was only available in a dissolved form in the oceans, but as weathering continued to happen on land, more minerals were available so that plants that had previously lived in the oceans were able to get those same minerals and nutrients out on land as weathering happened and made those small pieces more available and created soil. So that's another reason that weathering, or that this feature of this property of water is so important, that it expands and then it creates cracking and it has made minerals available for plants on land. One of the problems with this feature is these potholes, right? So if you live in a northern area like we do, you may have seen some of these potholes in your area. And what happens is water fills up in this, maybe even salty water. If you've thawed the water a little bit by adding salt to it, then it doesn't take as, it becomes liquid again, right? It's not frozen at the same temperature. So you get liquid water in this hole, and then the temperature drops and that water freezes. And as we have seen in that pop can, water expands and it creates new cracks. So you can see some new cracks that have occurred here. And pretty soon you get a big pothole, a lot of breaking up. Really what has happened is all of these cracks have been formed as the water froze and pushed away. And you can see in areas where there are small cracks, pretty soon we'll have water freezing in those, and then they will expand and they will continue to crack. This is again a reason, if you work for a city or if you live in a residential area, you may see in the fall road workers come through and put sealant in a lot of those cracks to try to prevent the water from getting into those cracks and then doing this freeze-thaw cycle and creating potholes. This might be a reason why you would want to reseal your own driveway or seal up any cracks in your own driveway so that you don't experience potholes in your own driveway. Now, in one of the activities that we did, and perhaps you have seen if you've driven over a bridge, you've also seen the expansion joints there, right? And that's because of those other materials cracking, but it's also another way, those other materials expanding, but it's also another way to allow the water to get through the bridge and through those joints, those expansion joints, so that they don't do a freeze-thaw cycle in some of those places as well. All right, that is the exception to the rule. Water expands and contracts differently. Water expands when it is frozen, when it becomes a solid form. Most other materials, those molecules slow down their movement and come closer and closer together. But water creates this lattice-like structure and gets slightly less dense when it hits that frozen state.